From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
You don't see very many additively manufactured products. People who buy things, we all buy things, right? We are all consumers or customers at some point in our life. And how often do you buy something that it was made by additive manufacturing? I mean, I don't know about you. I haven't bought anything. I've been waiting to get a pair of those Adidas, whatever they call those, Shape 4 or whatever the word is for those, their new brand. I've been trying to get with the carbon midsole, but I can't get those. They're hard to find. And then when I do, they're more expensive than I want to pay for things at the bottom of my feet. But still, they're hard to find. So people don't expect it as much as they might for things they buy. They know, oh, that's a molded plastic part, or that's we could tell that's a bent piece of metal. So they don't see, really unique, any otherwise unobtainable geometries and things that they buy. That's starting to come and be more prevalent. And that question will likely get asked more in the near future than it has been in the past, even in the recent past.
That was Al McGovern. Al has engineered products and built strong mechanical engineering teams in 6 different industries at 7 different companies in 6 states over the past 40 years. During that time, he's used many subtractive and, since 1991, additive prototyping methods in both research and in development efforts. In additive, he used equipment from 3D Systems, Stratasys, EOS, DTM, Z-Core, Carbon, Markforged, Desktop Metal, Formlabs, and HP. He's an advocate for early and frequent use of 3D printing in product development, from ideation to field trials, and is still seeking his first production 3D printing use in high-quality consumer audio products. He's a director of mechanical engineering at Shure Incorporated. All right, welcome to the show, Al. For those of you who may not know you or are familiar with some of the work you're doing, do you want to just share a little bit about where you got your start and what you're doing now?
Well, Mike, yeah, thanks for having me on. It's always great to talk to you, even if I can't see you. So I go back quite a ways, I guess, many hairs ago, as I like to say, instead of years anymore, measuring by hairs. I got out of college in '78. I'm an East Coast guy and got my start there. And it was in the early 90s, specifically 1990, when I brought Pro-E into the company I was working with at the time. And quickly discovered these files called STL, whatever stereo tessellated something or other. It was like, holy smokes, what is that? And then this thing called SLA. Like, what's an SLA? Named for the apparatus, right? Thinking, gosh, what is all this about? And so it was in 1991 when I was introduced to stereolithography. And worked directly with the people in Valencia, California, to print the first parts that I was going to use, because it was an R&D project, going from what we call today art to part. And so, long story there, but it was very, very successful. And Pro-E to stereolithography parts to investment casting without a single drawing. And very accurately done. So we did a lot of measurements. I have a great report for it, but it's all analog, all photographs and transparencies, but very well done. And it really had great promise to me about what this industry, which was known then as rapid prototyping, what it had to offer. And when I showed it to a few of the folks in the office, they said, well, here, what other things could we do? Next up was rigid waveguides. The company I worked for, Norton Systems, was famous for radar. Bomb sights in World War II, the electronic version of that these days is radar. And radar arrays get their power through what's called rigid waveguide. So WG and a number for the size, and very expensive to prototype because there was no way to rapid prototype it. So we could quickly 3D print a non-conductive version, but could we metalize it to make it conductive? And then could we metalize it in a way that was smooth enough on the inside so it could conduct the RF energy without attenuating it too much? So didn't know, but we tried it. And that was when I first met Dick Aubin. He was at Pratt & Whitney, and he ran the United Technologies Rapid Prototyping Consortium. So that was in 92, 93. And Pratt was making 3D, SLA waveguides, SLA turbine blades on the Beta SLA 500 that they owned. And they were plating them and doing testing with it. SLA was very popular in those days for that purpose. You could 3D print an exhaust manifold, and it would hold up long enough for you to get real good data, acoustic data and flow data. So it was already real popular. So I thought, I'm going to do that. And that was cool. We never quite got that across the finish line, but nothing to do with the technology there. It was just the plating couldn't do. Plating can't make a right turn in certain ways consistently. So it was a really excellent project, and that was another great way. Then we looked at the next step. That's when I met Emmanuel Sachs, Ellie Sachs, who's the father of metal 3D printing. He was a professor, I guess at that time, associate professor at MIT there in Massachusetts. And I saw his lab where he was just developing, putting the finishing touches on the metal laser sintering, what's today called DMLS. And it was very cool to see all of that and be right in the sort of the center of the universe of metal 3D printing. It was very, very impressive. And all of that, Mike, just created a burn in me that this technology has great promise. And then, other things came out, right? SLS was born in that time. I got some of the very first SLS parts, and the promise there of, the original material. Like now we could use nylon. Oh my gosh, this is great. These are thermoplastics. Didn't do so well. The resolution was poor. The granularity was high. It just didn't meet the promise at all. And then FDM came out, and that was cool. Extruding this string of plastic, but it was a string of plastic that you could just as much unwind and peel apart as easily as you put it together. So it had its place, and all of those things did. The urethane castings, started to use those, really like those. And then along the way, different things, smaller things, injection mold tooling that was done with 3D printing, or then early metal 3D printing that made little mold inserts and stuff. All of that, great promise, but it didn't always deliver the goal of production parts. But so that long answer, a lot of work there, a lot of time under the water under the bridge to produce the knowledge I have today, where the industry has come so far. And as you say, there's we were talking earlier about how people, maybe there's so many choices now. It's almost hard to know which one to use, and you can really be very specific about what you want for your 3D printer and get the very best one, which can do great things. You don't have to buy one and try to make it do everything. And I think that's a nice change in the industry that we've seen certainly in recent years.
And so as you described your experience with the various 3D printing types and materials, was your vision of using it always in production, or did you see it more niche as kind of prototyping? This is going to help me for this one-off project or this one-off product?
That's a good question. So it was immediately apparent this was awesome for prototypes. Before this, how did we prototype? Everybody had balsa wood and a set of knives and straight edges and glue. Everybody could, we could machine lucite or plastic pieces and glue them together. You might even thermoform something if you wanted to get an organic shape and glue it together with lots of reinforcements on the inside to get the things you wanted. And you could always machine, of course, right? Subtractive manufacturing was always available, but it was really clumsy. and it wasn't easily done. And you generally couldn't take your 3D CAD and just drive it to a part. You might have to break it apart and do different things. It was very obvious right away. It was Star Wars to me, right? Star Wars had just come out, and this was Star Wars to me. Like, man, oh man, this is a laser making a part. I never saw this before. So I knew I could prototype really easily. But what do you always try to do with, again, what do engineers do? We were talking about this earlier. You always want to do one better. Okay, I know I can do this, but can I do that? What if? All engineers ask that question. And we all wanted to, I know I wanted to get to production. That's why I did the investment casting. I mean, that literally was a production process. It went from a CAD model to an actual investment cast production grade part without any drawing. And that was phenomenal. Like, okay, and again, can I do that with metal printed waveguides? I mean, could I do this? Can I really get there? That was the goal, because production is expensive. Going to production is expensive. Tools are expensive. They take a lot of time. If I didn't need that time, money aside, if I didn't need that time, instead of 16 weeks to get a production tool, I could have my production parts in 4 weeks. Well, that gives me 12 weeks. Give an engineer an extra 12 weeks. What do you think they're going to do? They're going to iterate some more. So that was what I was always shooting for, Mike. The holy grail to me was production. And I would say certainly not SLA, but the SLS process, when it came out, that was the promise. That was the future. That was the intention. That's why they offered a palette of 6 or 8 or 12 different materials right out of the gate with promise of metal to follow. And, okay, great. This is awesome. So it's always been production as the holy grail. I like to look at it in those terms, because prototyping was a slam dunk. This was tremendous for taking something that was in a virtual space and making it physical, because I learned this early on in my life as an engineer, and then as a homeowner. Not everybody can look at a drawing and understand what it means in the three-dimensional space. But everybody can touch a three-dimensional part and understand, oh, now I know what you mean. So it's the ability to communicate enhances for each dimension you add, right? 1D, 2D, 3D. And we talk about 4D now, right? Time changing, the shape and all. The more you can do that, the more dimensions you add, the more senses you incorporate into it, the better off you're going to be in making that communication clear. So, yeah.
Do you think people underestimate the jump, though, from prototyping to production, both in the machines and the testing required to fully validate a material or a part?
That's a hard question to answer in generality. I think some people have underestimated that jump. I don't think people, like in a general term, do, but I think some people have. And I think the maker business was something along that line. It was like, this can't be that hard. Look, we're just going to extrude these fruits or these vegetables or this biomaterial or whatever. Well, it can't be that hard, right? And you find out that, because I found this out in my lifetime, right? I say this very often. Some people who hear this will probably moan that I brought it up again, but most people who think they know product development don't really know new product development. And unless you've lived it, you don't know where the pitfalls are. It's not automatic, right? Nothing is really automatic. There's always some effort. And I think people who have experience in that understand there's a little bit of vetting to be done here. So if you're open to that notion that you really want to prove it out and vet it properly, then you know that jump is a little bit larger and a little bit longer than perhaps you were, plan for a longer jump. If it's shorter, no problem, right? But plan for a little bit more work than you might otherwise think. But people do misjudge it. There's no doubt about that.
And going along those lines, have you had any experience in your career? I mean, you're knee deep in engineering every day and the day-to-day elements of product development and new product design, with technologies like 3D printing and other things that are hitting the news or can be more hype driven, do you get feedback from other parts of the organization to say, hey, why aren't we using this technology, or why aren't we going down this path? Why aren't all our new products 3D printed?
Wow. So perhaps I've never been asked that question. I think the answer I'm going to say in general is no. And the reason is you don't see very many additively manufactured products. People who buy things, we all buy things, right? We are all consumers or customers at some point in our life. And how often do you buy something that it was made by additive manufacturing? I mean, I don't know about you. I haven't bought anything. I've been waiting to get a pair of those Adidas, whatever they call those, Shape 4 or whatever the word is for those, their new brand. I've been trying to get with the carbon midsole, but I can't get those. They're hard to find. And then when I do, they're more expensive than I want to pay for things at the bottom of my feet. But still, they're hard to find. So people don't expect it as much as they might for things they buy. They know, oh, that's a molded plastic part, or that's we could tell that's a bent piece of metal. So they don't see really unique, any otherwise unobtainable geometries and things that they buy. That's starting to come and be more prevalent, and that question will likely get asked more in the near future than it has been in the past, even in the recent past. That's my take on it anyway.
Yeah, and jumping off that point too, is the design aspect that 3D printing allows is somewhat unique to injection molding or machining or forming, certainly. How is that impacting the product development cycle with some or most products I imagine have touched 3D printing for prototyping at least, but you have this element where sometimes you get more complexity if you use 3D printing, but your end product might be injection molded or some other conventional manufacturing. Do you think about that in any different way?
You have to, I think. If you have a view, we're working on something right now that we hope to be production 3D printed, and it offers, you can take off all the criteria basically. I mean, as a designer, you can almost take off all your criteria. Just what do you want it to be, and just we'll make it. And so that's kind of a novel way to look at it versus starting with so many constraints and then peeling away the constraints as you are able to, or pushing the constraints as you must, as your design matures more in the process. So there's that. There's a couple of ways I look at it, right? From in the making a part in 3D, a truly 3D printed part, as everybody says, you can make any geometry, basically. Obviously, there are limitations, but very few. And if you, and one of the common ways that is done, right, is with latticing. A very impressive technology, very cool technology, as I look at it even. But latticing a design can only work when you have enough thickness of your part to make that so, or it's not an exterior part. So in some industries, and a lot of my life has been spent with electronics and things that want to be smaller. For that industry, there aren't many opportunities where 3D printing can benefit you in terms of lightweighting or latticing something that lets you have the most effective and efficient design, because you need a contiguous, smooth surface for customer interface, right? I mean, I work at Shure, and that's microphones. So those have to be grippable and smooth. Now, contours in them, right? Notches or places for hands or fingers, that's a novel thing. Doing that in molding or casting would be impossible, or practically impossible, I would say. But in 3D printing, maybe so. Maybe you can 3D print the part to match the hand imprint of the performer. Because I'll tell you, performers' hands, as we see from custom mics we're asked to make time and again, they are from the size that will crush coal into diamonds to the most delicate hand you can imagine. And they want what is comfortable for them, because a microphone is something they might use quite a lot and hold quite a lot. 3D printing opens the door to that. But those are the two ways to me: the lattice work, which has limitations, and then the custom or really way organic shape that you can 3D print, which you can otherwise traditionally manufacture. And we have opportunity for those here, and I think people do as well. Bigger industries, bigger parts have way more opportunity for that kind of application. We don't have that as much here with the small. I think people who work with smaller parts can't do that all the time. And the resolution of 3D printing obviously suffers. There's only so small it can get before it loses some of that resolution of feature and what have you. So there are some limitations there too.
Certainly. And from the time you've started in the engineering space, 3D printing is certainly not all of your job. It's a technology you've touched in multiple ways. Have you seen a broad evolution of the technology? Is there a trend that you think it's going more towards production, or is there you see it continuing as kind of a nice tool for various applications, maybe low volume or particular applications, but still stuck in this over 20, 30 years, kind of this hype cycle that keeps repeating itself to some extent?
Yeah, so there's two answers to that. I break that answer into two categories: metal and non-metallic. Accepting ceramic, since you're talking 3D printing here, I don't normally make that distinction, right? You could say, well, ceramic is non-metallic. I have very little experience with ceramic 3D printing, so I really don't even care to offer any opinion or have any of my comments or opinions be applied there, because I don't really know that. But metal and non-metallic, so plastic, we'll say, there's two answers. In the metal space, I think it is closer and more of the promise. I've seen it move. Things are in production there, right? And I think that's very promising. It certainly isn't a technology or process for all, but if the benefits you can derive, so the lightweighting or effective, efficient design or creative design or any number of air, cooling channels or anything, you can do a lot of cool things with 3D printing. And in metal space, I think the opportunity to get you to production is closer. The understanding of the technology, at the molecular level, something I'm sure you would be better to speak to than me, has been much more evaluated and better understood. And even artificial intelligence is now being developed to assess the integrity of a DMLS part layer by layer. So it's really getting there, right? The non-metallic side, the plastic side, not so much so. And I see that as, because the same technology, right? There's a laser sintering plastic, there's a laser sintering metal. In that category, you could say the same. Even the extruded metal parts, the desktop metal and such, Metal X, those guys that are MIM-like, there's somewhat of equivalent in the plastic side, extruded as well, or powder with a binder in it. But the raw materials are not at the same strength level, same material properties, metal to non-metallic. The metal powders, when there's laser sintered, you're getting just about the same properties as wrought. not so in the plastic space. It's not there yet. And at least in my experience, it's not there yet. Now, it doesn't mean all properties. I'm talking about the ones that are relevant, and it's different for everybody, right? What's relevant depends on what you're talking about in terms of a product and its industries and how it's used. I'm answering you from a high-end, high-quality, rugged products. That all of my life has been in that space, not just the different companies, but all at the top of their game, right? Defense industry or ultrasonic welding or beard and mustache trimmers or telecom products, or now here at Shure. It's always been the top players. And so 3D printing for production, there's a much steeper hill to climb, more gates to go through before you get there. And I think the metal space has gone through those in a lot of these industries. And I would be very confident using it technically and structurally, but the cost, of course, target doesn't work in the consumer space. You can probably make 3D printing work in low volume plastic, but the properties aren't quite there. And that's, as well as I do right now, because we're using your talents for this, we're trying to make sure that we're vetting it properly so that when it goes out in the field, it has the lifespan and is able to be used the way a traditionally manufactured part would have been.
Certainly. And switching gears a little bit, and you can speak from this from any of the various jobs and positions you have, kind of as people are thinking about transitioning or even entering the engineering space to have a focus on 3D printing or maybe not, kind of, are there particular pieces of advice that you would share with them from the learnings you've had over your career?
Boy. Oh, gosh. You asked such short questions and I gave you such long answers. I'm good at that, I suppose. I talk to young engineers quite a bit. The folks here, I've reached a stage in my career where I have people that work for me now have their children starting to make a decision about college. So, hey, what field in engineering? And so they come see me. And we talk about a number of things. So as it relates to additive manufacturing, is that kind of where you want me to target the answer? Yeah.
Yeah, I mean, or I think that's a great place to start. But I know that's not the only part of engineering. So I feel like you can take it kind of either direction.
All right. Well, I'll begin there. So certainly in all the engineering schools today, there are 3D printers. And I think I know you definitely want to be familiar with it, right? I can speak for mechanical engineering, which is kind of where this technology has certainly found a home, right? In terms of the engineering space, mechanical engineering is where 3D printing is more often used. Other than, well, let's leave it there. So I would suggest they would do well to understand what the additive manufacturing technologies are that are out there, and learn as much about them as they can. Encourage them to learn how to create the 3D CAD, which is at the core of all things we do in mechanical engineering. At the end of the day, however you get there, you're going to need a 3D solid model that represents the part or an assemblage of parts in the product that you want to manufacture. And the accuracy of that CAD and how it represents what you want in its final state is really important. And we drive that home here because it forms the core of your intellectual property. So learn your CAD tools, learn your modeling skills. That is the way you capture visually and electronically all of the technology you've learned and the laws of physics that you have been somewhat trained to understand in college. And that you certainly will start to apply and then really come to understand in industry. So learn that, know your laws of physics, but know that you have to capture them in a way that can be communicated to others. And as we mentioned earlier, 3D is the best way to do that. A physical 3D part, 3D that's been 3D printed, quickly gets you something right off the gate. So understand that relationship, that cause and effect from this theory you've learned of F equals MA. How do you get it down to something in somebody's hand? There are a series of steps. be good at those. I think that's important. Be open-minded. I often talk about that. I think that's really important. The third thing, which has been more prevalent today than it was, in 25, 30 years ago, even when I was getting my feet wet with this, I wanted to understand a bit about the software, what made this thing work? How did it behave? What was an STL file, and how did it drive the tools? Just like G code. What is in a G code? What makes that language work for what? How do you talk to a CNC machine? What language do you use? And I always thought that was important because it helps you understand why the value, again, of what I said before, of all the accuracy of your model. You're going to translate it into something that this machine has to print or somebody has to machine, right? There's additive and there's subtractive. You could bend metal as well, but those are the basic methods for producing things. So the more you understand that, the better it is. Today, in mechanical engineering, I often suggest people get familiar with robotics and how to program robots, learn HTML, learn those things that let you operate in the space that is now getting to be digital, because everything is digital, and that's an important technology to understand, right? What does it mean, digital? Well, it means that there's ones and zeros that are defining everything now. So how are those ones and zeros captured? What language is used to tell a computer to run a certain simulation, or to tell a machine to cut this metal here and don't cut that metal there, or to tell a laser to turn on or to turn off, or a binder when to dispense a binding solution. Understand that. Same thing with robotics and automation. Understand, what's it going to do? How do you tell this robot? That's important if you're going to design and build robots, but if you're going to use them, that's also important to understand. I think the more you understand into the depth of the product development process, the better off you are. And so that was, in my day, I practice what I preach here. In my day, that became understanding these things called personal computers. So once these computers became available, and for $2,000 you could buy your own 8286 computer and be happy as all heck that you had one, with a small color monitor and a 24 kilobaud modem. You thought the world was your oyster. What makes it run? So I would learn DOS. I would learn the operating system. When I first got to do Pro-E, it ran on Unix stations. I still have my Unix System 5 book. So it makes a difference to know how that works. So don't just stay in mechanical. Don't just learn F equals MA. Learn why it does and how do you apply it to get to the part. Because mechanical engineers, unless you're writing a book or teaching, you're not going to get paid for talking about it. You're going to get paid for what you produce with that knowledge. And that's my whole space. My entire life, except for 1 year, my entire work career has been with companies that have manufacturing, that manufacture the things I designed. And so that's a long answer. Again, I'm good at that long answer to the short question, but understand the bigger ecosystem in which you are working, and software is a big part of that these days, because we are in a digital workspace right now.
Great. Well, excellent advice. And I want to thank you for being part of the show today, and we'll hopefully talk to you soon.
Oh, I'm sure of that, Mike. I have no doubt about that. Thanks again for asking me. It's a privilege to help. I hope some of the folks that hear this find great value in it, or even a little bit of value. If you help one person, then it certainly has been worth the time. Thanks very much.
Thank you.